A subway map. The first time you reach a station is already the fastest way there. Always.
Why?
Pattern 6 of 10 in the NBX STUDIO dojo. Breadth first search. It finds the shortest path, and the only reason it works is the order it visits things in. Your giveaway word is shortest, and it's almost always literally in the question. Minimum steps or fewest moves, which is the same thing wearing a different hat. Level order, when a tree has to be read row by row. Nearest or closest, which means distance again. But if the edges have different weights, plain breadth first search is wrong, and you want Dijkstra instead. And if you only need to know whether a path exists at all, depth first is cheaper. Shortest is the word. Everything else follows from it. You're standing at Station A, and you need to reach Station E in as few stops as possible. That map connects A to B, A to C as well, B to D, C to D, and finally D to E. You could hop on any train and hope, and you might get there eventually by a scenic route. Breadth first search is more disciplined because it refuses to guess. It checks every station one stop away before it looks at any station 2 stops away. Standing at A, the queue is our to-visit list, and it holds one entry. Visit A, 0 stops out. A deke is a list that's fast at both ends. Visited is the set of stations already queued, and it starts holding A. One queue, one set. Every breadth first search has both. The queue decides the order, and the set stops you going round in circles. While the queue holds anything, keep going. Queued pop left takes the station at the front and removes it. Front, not back, and that one word is the whole difference between this and the previous pattern. We take A at 0 stops. Is A our destination? Not yet. A stack hands back the most recent station. A queue hands back the earliest, which means the nearest, and that's why the answer comes out shortest. Now the neighbors. A connects to B and to C. For each one we ask whether we've seen it before, and neither of them has been. So we mark them visited, and push them onto the back of the queue, each carrying 0 plus 1, which is 1 stop. B goes on.
C goes on.
The queue now holds B and C, both at distance 1. That's the first ring of the ripple, and nothing at distance 2 can be looked at until both of these have been. Straight from the dojo. B and C are both in the to-visit list. Which do we check first? C, added last. B, added first. Or whichever looks closer to E. Have a think and pause the video if you'd like a moment. Ready? B, because it was added first. First in, first out, and that ordering is the entire reason this finds a shortest path. We take B off the front, 1 stop out, and it's not our destination. B connects to D, which hasn't been seen, so we mark it and push it on the back at 2 stops. The queue is now C at 1, then D at 2. C was added before D, so C gets looked at first, even though we're standing beside D. So the queue refuses to let's run ahead, which is exactly what keeps the distances in order. Now C comes off the front, also 1 stop out, and it isn't our destination either. C connects to D as well, and here the code does something that looks like nothing. D is already in the visited set, so we skip it. Without that skip, D gets queued twice, and on a map with a loop the search never finishes. D comes off the front at 2 stops. Still not our destination. D connects to E, and E is new, so we mark it and push it on at 2 plus 1, which is 3 stops. E is now the only thing waiting. Distances have climbed in order the whole way, 0, 1, 1, 2, 3. The queue kept them sorted without a single comparison. E comes off the front 3 stops out. Every station nearer than 3 has already been taken off and dealt with, so when we ask whether E is our destination, and it is, we return the distance it carried, 3. We compared no routes at all, because the first arrival is the shortest arrival. Here's what to remember when you're tired and under pressure. Take from the front and you've breadth first search, which fans out in rings and gives you shortest. Take from the back and you've depth first search, which dives down 1 branch. Pop left is BFS. Pop is DFS. And BFS costs memory because a wide ring is a big queue. Same code, 1 word different, completely different answer, and that trade is worth naming before anybody asks you for it.
For to go and do.
Binary tree level order is BFS with the rings made visible. Number of islands is BFS on a grid rather than a graph. Rotting oranges is the one where the rings are literally time passing. And word ladder is the hard one, where the graph isn't given to you and you've to build it. 3 things to take with you. Your signal is shortest or minimum steps. Reach for a queue and a visited set, always both. And the reason it works is that the first arrival is the shortest arrival. Next in the dojo is depth-first search and backtracking, the same code with one word changed, and a completely different personality, because taking from the back turns rings into a dive. Go and do level order first.